So hello everyone. The plan today is to actually go over the two challenge questions that I had given in homework last night, just in case some of you got stuck on them or weren't able to do them all the way through for whatever reason. And then I'm going to do a little bit of new stuff near the end of the period as well. So, just to make this go a little faster, I actually wrote out the entire solutions for these two first questions. I'll just read through them. I'm going to go a little bit quicker, but you can always go back and rewatch the video if you need to. So, okay, before I start, anybody have any idea what selfish reason I might have had to assign this first question? Nobody? So the reason I assigned this first question is because I love physics, and this is basically a physics question. Anytime you have speed, distance, and time involved, you're going to be dealing with physics usually. So the idea is you have this fly sitting on the wall 100 centimeters above the spider. The fly starts to move at 10 centimeters per second horizontally, and then the spider 1 second later takes off along the wall and has to try to catch the fly. So obviously the spider's going to have to move at an angle with respect to the fly to get to catch the fly at this spot here. Okay. Now there is a lot of stuff happening in this question. The very first thing is that you've got centimeters per second and centimeters as your values for your units. You cannot work usually in a question with two different units like that. So we're going to have to consolidate that into one unit. And the unit we're probably going to use is centimeters, because the 100 centimeters is like a constant value that they gave us for the length of this side. This is a right angle triangle, so we probably are going to be using some sort of right angle triangle trigonometry. And usually that's with side lengths, not with speeds. We also have a time reference. It says that after 1 second, the spider begins moving at twice the speed of the fly. So that means that if the fly has been moving for a certain amount of time, the spider has less time to move that a certain distance to catch it. And time is going to be one of the main aspects of the question, but so is distance, okay? So I'm going to go through how I solved this, and I may have solved it in a slightly longer way than you have, because I wanted to show you, continuing the idea from yesterday of not putting numbers into a final equation until you're ready to actually solve it. I used variables almost all the way through, okay? So the 100 centimeters is a big clue. We have to work with side lengths or distances, but we're given speeds. So how do we work with distances if we're given speeds? Well, v is velocity, which is also a speed, and I'm going to call it velocity from now on, is equal to distance over time. So if I want to convert a velocity into a distance, I have to rearrange the equation to get d all by itself. That means the t is going to go over here and multiply, and we get d is equal to v times t. But the spider leaves 1 second after the fly. So how do we put that into the expressions? Well, what I did is I called the time for the fly t, and I said if the spider is leaving, exactly, chat, if the spider is leaving 1 second after, that's t minus 1. Okay, the time of the fly minus 1. So that relates the two times of the two insects together. Oh, one of them's arachnid, sorry. And then if I put that into the equation, d is equal to v times t, we've got v times t for the distance the fly travels, and 2v times t minus 1 as the distance the spider travels. Now, why is it 2v? Well, they said that the spider was moving twice the speed of the fly. So I know that the speed of the fly is 10, but I want to just use it as a variable v in this question, okay? I don't want to input the numbers in until I'm ready to do so. And because it's twice the velocity of the fly for the spider, I wrote 2v here. I replace t by t. I replace t over here by t minus 1. Okay? So we're going to use the Pythagorean theorem to relate all those three side lengths. Let's put all of those values into the Pythagorean theorem. Now, I may have lied a little bit. I am going to use the 100 as the number for the b length, simply because I want you to see where that 100 goes in the formula. But I replaced a squared by vt, which is the distance the fly travels, and I replaced c squared, which is our hypotenuse. So if I go back to the picture for a second, the hypotenuse is the distance that the spider travels. So that is going to be 2v times t minus 1 squared. Okay? And what I did here is I started to expand. So I brought the square in. Because these are multiplying, it just becomes v squared t squared. Now these are also multiplying. So I did this in 2 steps, and some of you may have wanted to do it in 1 step. I brought the 2 into each factor, which gives us 4, 2 squared, v squared, and t minus 1 squared. Now you could have expanded that at the same time. I just chose to do it on a separate line so you saw all the math going on. And at the same time, for this line, I brought the v squared t squared over to this side of the equation as well. I temporarily left the 100 squared there just so that it wasn't taking up too much room on this side. Okay, I will bring it over to the other side in a second, and you'll see why. So what I did is I expanded the t minus 1 squared, multiplied the 4v squared into that bracket through distributivity, and I noticed that the 4v squared t squared matches in like terms to the minus v squared t squared over here. So I'm able to collect like terms and get this statement here. So I didn't carry the 10 or the 20 all the way through the simplification. I just carried v throughout the whole simplification, and it's going to take care of all that stuff for me. In fact, I'm only going to have to type in the 10 for v's now. And at the same time, I brought the 100 squared over because this is a quadratic. And the only way you can solve a quadratic is by making it equal to 100 first, and then using either factoring or the quadratic formula to find the zeros. We're not looking for a maximum here. We're looking for zeros, so I would not complete the square here. So I put the 10 in where it's supposed to go. I expanded all of that stuff. The 400 minus 10,000 joined together. And we end up with this expression. Now, I noticed that this expression, everything is divisible by 100, so I actually factored that 100 out. Now, before we get to the rest of the solution here, I wanted to know if I was on the right track. Okay? So if I had made a mistake and I continued going, I would just be compounding that error and I wouldn't potentially get to the right answer. So I wanted to check to see, like, what happens if this thing isn't factorable? And I didn't want to use type 2 trinomial factoring because 3 times negative 96 is going to be a pretty big number, and I didn't want to spend the time to do that. So I was thinking to myself, well, what would be a quick way of checking to see if that's actually factorable? Now, I feel like I've introduced a website to you before called Wolfram Alpha. And I know that there are apps out there that you can take pictures of things and they'll expand and solve and all that stuff for you. And I want to point out that this is technically not cheating, all right? Because I don't know what the answer is going to be. And I'm not asking it to tell me what are all the steps to answering the question. I'm asking it to tell me, am I on the right track? Is there actually a solution to this quadratic? All right? So there's a difference between getting a program to show you all the steps and just checking to see if you actually can find an answer to what you've been doing. So if I did this right, I had typed this in period 3, so I just copied and pasted that. This is just the equation that I had on my smartboard, right? It was 0 equals 100 times 3t squared minus 8t minus 96. That's what I had factored it to. If I press enter, after typing in solve, Wolfram Alpha is going to do its magic here, and if everything works out, it's going to tell me that yes, there are 2 solutions to that quadratic, and it even graphed it out for me, showing me where the 2 zeros are. And because we're looking for a time value, I need a positive value, and there is a positive value. Now imagine for a second I had gotten two complex roots here. If I had gotten two complex roots here, I would have known that I had made a mistake somewhere, or potentially that the question is wrong, right? And I wouldn't want to continue until I figured out what that mistake is. So that's all Wolfram Alpha is doing here, is just confirming that you are on the right track. There is a solution here, so keep going. So it's a really nice tool for that. And as you saw, it works pretty smoothly. So, you know, if you've never used it before, put it in your arsenal of tools that you could potentially use. So let me go back to my smartboard here. So once I did the Wolfram Alpha calculation, I'm like, okay, let's now solve it. So I decided to use the quadratic formula, which means using my discriminant first. So doing the discriminant, b squared minus 4ac is the discriminant. I found 1,216, and that tells me that there are two zeros, right? I then plugged it into the rest of the quadratic formula. So minus b plus or minus the square root of b squared minus 4ac over 2a. So minus b is minus negative 8, which is positive 8, etc., etc. And then I did something that we did in our radicals section. I took the 1216. Now, I've got to admit that looking at the Wolfram Alpha number did help me kind of figure out that this was possible. So there might have been a little bit of cheating there. But I figured out that 1216 is actually got a number that's square rootable hiding inside it as a factor, which is 64. So 64 times 19 means I can pull out that 64. And when you root 64, it gives you 8. So you're going to end up with this. And then I just decided, well, instead of factoring, which is normally what I would suggest to do, I understood that, you know, I can divide all three of these by 2. And that gave me 4 plus or minus 4 root 19 over 3. It's not the exact same answer of the Wolfram Alpha. They actually factored out the 4. I chose to not do that because I'm ready to find my actual time value. And at this point, I do want to have a decimal value because I'm going to use that to calculate other values with it. You could have left it in this format. You'd want to know which one is the positive one, and clearly it would be the one that's adding, because if you subtract a number that's slightly bigger than 4, you're going to get a negative number. Okay, so it has to be the 4 plus 4 root 19 divided by 3, which is our time value, which gave me this. Let me just do this. Okay, so I found that t is equal to 7.15 seconds. Then I substituted that back into my equation. Now, I actually noticed in period 3 that I had made a mistake, and I guess the mistake didn't get corrected here, so let me do that right now. I forgot that this was t minus 1. So it would be 6.15 over here. I'm going to have to calculate that. So what is 20 times 6.15? That gives 123, which I should be able to have done in my head. Okay, so the distance that the fly travels is 10 times 7.15, which is 71.5 centimeters. 10 times 7.15 is 71.5 centimeters. 20 times 6.15 is 123, which is going to make me have to change this picture as well, which is also going to have to make me change how I figured out the angle that the spider is going at. So I can't remember, but I think it's somewhere around 33 degrees, if I'm not mistaken. Somebody can correct me if I'm wrong there. I don't feel like recalculating it again. But yeah, that's the solution to that question. So I had stated that it's like a 4++ level difficulty. There is a lot going on in that question. From the quadratic, it's 35.5. Okay, thank you, chat. So I'm actually just going to round that off to 36 degrees. Okay. So it's a great question. It's got a lot of aspects of all of the different kinds of math that you've been doing probably since grade 9. Not all of them, obviously, but a lot of them. including some of the rational stuff we did this year. So it's a really interesting question in my opinion. So I went through it pretty quick, but you could always just rewatch this video if you needed to, if you do end up wanting to try it yourselves, or if you end up seeing a question similar to it in the future. So here's the other question. This one was much easier. Find the diagonal length from this corner to this corner. Now, I actually didn't solve it with the 4s. I just solved it with a cube side of A, because if I get to that formula, then we could just plug 4 in for A anyway. But I did draw out the way you would have to break this down to be able to solve it. And a keen eye will notice that this is basically the same type of question as the question with the pillars of rock out in the rivers that we were doing in the word problems, where you have a triangle that's on the flat horizontal plane, and then another triangle that's on a vertical plane, and both of them are sharing a side length, which is this dotted line here. So I just did it all with A's instead of 4s, and what we're going to do is we're going to find the common side length using the Pythagorean theorem. So the right angle triangle tells us that this side is the hypotenuse, the dotted line is the hypotenuse. So if I calculate that hypotenuse as C, subbing in A for both the lengths A and B, because they're 4 and 4, or A and A, you get 2A squared, and then square rooting that for C gives you root 2A squared, which I simplified to A times root 2. Square rooted the A squared, brought it out in front. And what's interesting is that hypotenuse for the first triangle becomes one of the regular legs of the second triangle, and X becomes the hypotenuse of the second triangle. So I subbed all of that into another Pythagorean theorem. So X squared is now my new hypotenuse, C squared is one of the regular legs, and A squared is the other side. Putting in C squared, which I could have just gotten from C squared itself instead of squaring the last answer there, so that's 2A squared. That gives 3A squared when you add them together, and then square rooting gives you A times root 3. So this is the equation that would work for any cube. If you have a 4, you'd put a 4 there. If the side length would be 10, you'd put a 10 there. And this is the general equation for the diagonal length through a cube for any cube. So I like those two questions. They're very interesting. They allow you to, and they're, I mean, it's funny, neither one of them used SOHCAHTOA. Both of them were just Pythagorean theorem questions, but you know, especially the spider and the fly question, just how complicated a Pythagorean theorem question can get is pretty impressive if you think about it. Okay, let's move on. And now we're going to start the actual lesson for today. So I had asked you in the Google Classroom if you could potentially go and print off this page in preparation for today's lesson, and if you were able to maybe try to fill it out as well. If you weren't, that's fine. I'm going to do that for you right now, but I'm not going to do it by hand with a calculator. What I'd like to do is go to a spreadsheet and show you how you could do this with a spreadsheet and save yourself an enormous amount of time. It's not that I wanted you to waste time with your calculators. I did want you to see the values before coming to class if possible, and maybe try to figure out what the patterns were in this table. But if you didn't do it, or you know didn't have time or whatever, I'm about to do it anyway. I'm just going to do it on a spreadsheet, okay? Okay, so I'm actually going to erase these for a second and show you the power of a spreadsheet here. I'm hoping you can all see this okay. Everybody in period 3 said that there was it was okay to see, and yes, there are a lot of patterns in here. But if you haven't worked with spreadsheets, I think the higher you go in math and science, the more you're going to work with them, and the more practice you see, you know, somebody showing you how it works, I'm not sure if you have access to a spreadsheet at home right now, but if you just follow along, and you'll know that this video is up there somewhere, you could always go back and look at it if you had to. But if you look at the first table, the first column of the table, I should say, which is the angle column, it's going up by 15 degrees. So watch what I can do. If I press 0 and 15, that spreadsheet now technically knows that I want to go up by 15. It only knows that, though, if I select both of those cells, go over to the corner here, and start dragging down. It has now automatically filled in all of the angles going up by 15, past where I needed to go, because I had to finish at 180, so I'm just going to delete those. Okay. Now, the other usefulness of a spreadsheet is to do multiple calculations. And I could actually get this spreadsheet to generate the sine value of all of those angles and then just copy down that one equation instead of having to type it out each time. But I want to show you something about spreadsheets. Chat. Does anybody know offhand what is the sine of 30 degrees? That is correct. So some of you, I'm thinking, because of how quickly you answered, that you didn't even have to type this into a calculator, that for some reason you already know that sine 30 is equal to 0.5. It might even be for some of the homework questions we've been doing recently, okay? That is, and the reason that you know that is because 30, 45, and 60 are degrees that are used quite often in trigonometry. So some of you may even know the sine of 45 and the sine of 60 that quickly as well. They're not quite as nice decimals as the 30, but I wanted to do the 30 because it gives a nice 0.5. So we know that the answer to this cell, if I do sine of 30, it's supposed to be 0.5. But I want to show you what happens when I start to type this in. So to show a spreadsheet that I want to type in an equation, I have to start with an equal sign. Okay? And I want to do the sine of 30. So as soon as I start typing sine, the spreadsheet knows what sine means. And it's even telling me right underneath here, sine of an angle, but then it says provided in radians. The spreadsheet is programmed to use radians as the measure of the angle. So if I say, okay, well, do the sine of 30, and let's say it didn't tell me that and I didn't know, as soon as I put that, so what I'm doing here is I put a bracket to tell the spreadsheet, okay, what I'm about to type in next is what I want you to do the sine of. And I selected the cell that contains 30. So the reason it's putting an A4, and this is what I'm worried you might not be able to see very well, folks. It is fairly small. But that A4 is referencing the value that's inside the cell A4. Okay? I'm going to close the bracket. And it is not giving me 0.5. And the reason it's not giving me 0.5 is it thinks that 30 is not a degree value, but a radian value. Now, I know some of you don't know what radians are yet. It's just another measurement system for angles, and it's a measurement system for angles that is based on the decimal system. You see, angles in circles are not based on base 10, they're based on base 60. So they're technically not decimal values. Your calculator takes care of that when you do sine or cos or tan. And in fact, there's more complicated explanations for this that I don't want to get into right now. But the spreadsheet is programmed to use radians. And I want you to think about that. This is a software that people use all over the world, and degrees isn't the standard. That's how important radians are. And I'm actually hoping to show you radian angles a little later on. But for right now, we've got to fix this problem. How do I get the spreadsheet to give me 0.5 when I do the sine of 30? Well, if I click here, which allows me to click there, there is a function that allows the spreadsheet to understand that I need it to convert 30 into radians and then do the sine of that value. So I'm just going to put that function right in front of A4, and that function is conveniently called radians. Okay? And I'm going to open and close a bracket around the A4. And what that's now saying is take the sine of the converted 30-degree angle into radians and give me the answer. And you can already see the answer being displayed there. And if I press enter, now I've got 0.5 as my answer. So it is possible to do sine, cos, and tan values on a spreadsheet, but if you're using degrees, you have to first convert them into radians by using the radian function in front of the degree value. Okay? Now, all of that was not why I wanted to show you spreadsheets. The reason I wanted to show you spreadsheets is now that I have that calculation in that cell, if I go down to the corner, click on it, and drag down, it's going to do the calculation of all the sine values, and if I drag up, it's going to do all the sine values above, and I now have all the sine values that you calculated by hand if you did that handout, all done within seconds, as long as you understand how to type in the first equation. Now, let's start talking about the patterns here. I want you to look at the answer you're getting here and the answer you're getting here. The answer you're getting here and the other one here. That's the first pattern, and probably the most important pattern in those numbers. Look at the angles. Somebody's already noticed. Okay. Both of those angles add up to 180. 60 and 120 add up to 180. In fact, if I keep moving one outwards, they're always going to add up to 180, and those angles that add up to 180 give me the same answer for sine. Now, what word talks about angles that add up to 180? That's right. So these supplementary angles, for some reason, give us the same value for the sine of the angle. Now that's going to have some pretty important implications later on, and I'm just going to give you a little bit of foreshadowing here. You've already seen the sine law, and we're going to be seeing the sine law again this year. And the sine law can be used to find angles. Now, if you're trying to find an angle, you'd be arc sining 0.8660. But there's two answers to that angle. Okay, there's 60 and there's 120. So when you arc sine 0.8660, how do you know what's the correct answer? Your calculator just gives you 60. Why doesn't it give you 120 as well? And this is going to have some serious implications on some of the triangles we're going to be solving using the sine law to find angles. And that is called the ambiguous case of triangles. And I'm going to admit right now that the ambiguous case, along with probability, is probably one of the hardest things for me to teach, because I didn't learn about the ambiguous case until I was in teaching high school. I never learned it in high school. I don't remember learning it in university. And my brain, you know, you can't teach an old dog new tricks. When I started having to teach the ambiguous case, it is taking a long time for it to sink in, and I still struggle with it. Okay? So anyway, that's coming up very soon. So you're going to get to see me struggle when I start teaching you the ambiguous case of triangles. Some of you may understand it better than me already. I do understand it. I just find it difficult to teach. Okay? But it has to do with this idea that two angles can be the answer of the same sine ratio. Okay, so we're going to discuss in a minute why this is happening. Okay, why are you getting these supplementary angles that are giving you the same number when you do the sine of them? Let's look at the cosine. Now I'm going to do a little bit of cheating here. If I copy this over to this cell by sliding the little corner over to this side, now I don't want to do sine anymore, I want to do cosine, but it's already set up to do the radians transformation, so I'm just going to select the sine and change it to cos. And I'm going to change the B2, because I slid it over, it immediately changed it to B2, but I still want it to be doing the cosine of A2. And now that I have that one done, I'm just going to drag down the corner. Bing, bang, boom. All of those are done. Now, what the heck is happening here? We're getting negative numbers now. It's still dealing with supplementary angles. And I don't know if you've noticed that the 90-degree angle here seems to be the tipping point, right? So why is that happening? Why is 90-degree angle the one where on either side of it, our supplementary angles give us the same values. But for the cosine, yes, the numbers are the same, but one of them's positive, one of them's negative. What the heck's happening there? And that's what I want to look at next. Okay? So in order for you to have this in your notes, if you have a Windows computer, I'm about to talk to you about another little trick you can do. If you ever want to put something into a document, even on Google Docs for like science class, history class, whatever class you might be in, there is a nice little tool called the Snipping Tool in Windows. I don't know what it is on a Mac. So if you go to the magnifying glass search on the Windows taskbar and type in snip, usually it's the first one that pops up. You won't be able to see it because I'm not sharing my screen here, but you'll see the result. I'm just going to copy this table and I'm going to bring it into the note. I'm going to replace, oops. So let me switch over here. I'm going to replace this by that. So now I don't have to fill it in by hand. It's all filled in for me. Okay. Now we get to this. And this was the second page that I asked you to print out or at least look at. So, what is this? Well, I'm not going to be able to fill the whole thing in. I don't want to take that long, but I'm going to show you with the green line what's happening here. So the green line is a 30-degree angle, the red line is a 45-degree angle, and the purple line is a 60-degree angle. I'm not going to write those all in because it's going to get very, very messy inside this circle. Okay? Now, one thing about all mathematics, folks, is as soon as a new branch of mathematics comes out, or has come out in history, they have to make sure that it works with all the other branches of mathematics. And if it doesn't, they have to find some way of explaining the differences. Like, for instance, complex numbers don't technically fit in with all the other math, but it can if you look at it and do things in a certain way. So what happens when you start doing trigonometry on an x and y plane? So this is the x-axis and this is the y-axis, right? If I draw a dotted line here, and I could do this for the red and the purple lines as well, I get a right angled triangle on the Cartesian plane. And this coordinate here on the circle is a very important coordinate. Now, to make one more thing you need to know is this is a radius 1 circle. Okay, so each one of these lines is a radius of 1. And it's a radius of 1 circle for now. That will change later, but for right now, it's basically called the unit 1 circle or the radius 1 circle. I have another name for it, which I'll talk about in a minute. So let's get back to this dot here. This dot is really important because if I measure this length on the triangle, we can call that the x length of the triangle, because I moved along the x-axis to get underneath that point, and then I can call this the y length of this triangle. And that makes this coordinate x and y. Nothing spectacular there. It should make sense, right? We moved along x and we went up by y. So that gives us the coordinate x, y. But let's look at the trigonometry of that triangle. If I do the sine of 30 degrees, well, SOHCAHTOA tells us that the sine is equal to the opposite side divided by the hypotenuse. Well, the opposite side is which side in this triangle? It's the y height. What's the hypotenuse? The hypotenuse is the radius of the circle. But even more than that, the radius is 1. So really, sine 30 is directly equal to y. So I now know what the number value is for the y of that coordinate. It's sine 30. Well, what about the x value? If I do cosine 30, what do I get? Well, the cosine is the adjacent over the hypotenuse. The adjacent side is the x side. The hypotenuse is again r, which is just 1, so I'm not even going to write it. And that means the cosine of 30 is the x value. of that coordinate. Now, one thing about this circle, which might throw a few students off, is that angles are always measured from the x-axis going counterclockwise on that circle. Okay? And that is a little bit counterintuitive, especially if you've ever done any type of orienteering. Orienteering is going out in the bush with a compass and trying to find your way with that compass and a map, right? In orienteering, the measurement of the angle is from the north going clockwise. But that's not the case here. In angles in standard position, the angles are always measured from the x-axis going counterclockwise around the circle. Now, here's where the magic starts to happen. What if I draw another line over here, and I'm going to change its color also to green. And there's a reason I'm changing it to green, is because it's the mirror image of that green line on this side. Let me just adjust it a little bit. I think it's a little bit low. So it's right about there. So that green line on this side is the mirror image of that green line. Now, when I talk about sides, let's actually name this stuff. We call this side the first quadrant. We call this side the second quadrant. We usually use Roman numerals for that, okay? So we're now in quadrant 2. Can somebody tell me what this angle would be? That's right. It's the supplementary angle, right? That angle is 150 degrees. So if I talk about this point, we'll come back to the 150 degrees in a second. We don't even need that to calculate, to figure out what the coordinates of this point would be, because we already know the coordinates of this point. Now, we already said that sine 30 is 0.5, right? That's the height of the triangle. Well, isn't the height of this triangle also 0.5? If we go back to our table, the sine of 30 is 0.5. The sine of 150 is 0.5. The reason that happens is because of this circle. Because the heights of the two triangles measured from the x-axis are mirror images of each other, so they have to have the same height. But one of the angles is 150 and one of the angles is 30. So this would be actually the sine of 150. And if you do sine 150 on your calculator, you're going to get 0.5 for that reason. Does anybody happen to know what the cosine of 30 is? Nope, it's not 1. That's right. It's 0.8660. Okay, you can check it on your calculators if you'd like. So this one's also going to be 0.8660. Wow, sorry. Let me rewrite that. However, it's measured this way on the circle. So what do I have to change for that 0.8660? That's right. It has to be negative because it's on the left-hand side of the y-axis. In fact, any angle between 90 and 180, and there's where the 90 degrees comes into play, right? It's separating the quadrants. Any angle greater than 90 and smaller than 180 has to give us a negative number because we're on the negative side of the axis, of the y-axis, right? And that would be the cosine of 150. And if you do the cosine of 150, you're going to get the exact same number as the cosine of 30 because they're supplementary, but it's going to be negative instead of positive. And that's the magic of this circle. Because if I now do the exact same thing with 45 degrees, I'm also going to know what the answer is for 135 degrees. If I do the exact same thing for 60 degrees, I'm also going to know the answer for 120 degrees. And not only that, when we go a little bit further, knowing 30 degrees will also tell me the angle for 210 degrees. Will also tell me the angle of 330 degrees. So just knowing 3 angles in the first quadrant is giving me 12 different angle values without needing a calculator, as long as I know the ones in the first quadrant. And the ones in the first quadrant are called the related angles. Okay? They're the ones that tell you what all of the other angles will be if you know those 3. And they're also called the special angles, and we'll talk about that soon. So I call this not the unit 1 circle. I call it the magic circle. Because it tells us all those things. And I haven't even talked about 90, 180, 270, 360, and 0 yet. Because we technically also know those if this is a radius 1 circle. And that's it for today's lesson. So there is no homework tonight besides getting very comfortable with how this circle works. Okay? I just want you to understand the mirror image idea and how some of the values are going to be negative and some of them are going to stay positive, and maybe even try to figure out what the other ones would be on around the whole circle for even 45 and 60 degrees. You can use your calculator if you don't know what sine and cosine and sine of 45 degrees are. Same thing for 60 degrees. But we're going to come back to this and talk about it a little bit more. There is one more slide for today, but that's enough for today. We did a lot of work today. Okay? So if you need to watch this video again, whatever you need to do to get comfortable with that circle, that's what you need to do for homework.